here, right, so this is a little more verbose. So the idea here is that stuff that's in purple is places where the actual notation is a little suboptimal. It's slightly, more awkward than the optimal one that was designed. I mean, this is not generally usually an executable notation, though you could make it executable. It's just a notation, it's just a syntax. But this is stuff you can run. So what do we have here? We have the fact that this thing is we have to type a few more characters, and we have this dot, which is a statement separator. A lot of languages at the end of statements, you have to put a semicolon usually, but in this case you put a dot. And the dot has nothing to do with the problem at hand. The dot is a constraint put on you by the programming languages for its own dark purposes. To keep the implementer sane, or to disambiguate something else, or for problems that the language in general has to deal with, but which are not really part of your problem here, which is expressing a rule about syntax. On the other hand, we can use a standard notation, and we get a lot more purple stuff and a lot of red stuff. Right? We have these parentheses everywhere that express absolutely nothing. What they're telling us is that there's a parameter list and it doesn't have any parameters in it, and you might ask, well, if there are no parameters, why do I have to say so? Well, we have our reasons. We have to disambiguate this from variable references, whatever, right? None of this has anything to do with the solution. It has everything to do, the other way around. It has nothing to do with the problem you're trying to solve. It has everything to do with the solution that you've chosen. To use this particular language with its constraints, it forces you to deal with a lot of irrelevant cruft, right? And that is really something that you can judge syntax by more objectively as to whether it's doing its job. And again, an Alan Perlis quote is always, right, almost any programming language topic you'll find a good one. But this is deep, right? The fact is that if the language is making you deal with stuff that isn't relevant to your problem, that's a burden. That's something that's low level, that makes it harder to work with. That's something you want to avoid. This is true not only for syntax, of course, but started with syntax because that's what people obsess about. But as I said, Parkinson's law of triviality, it really shouldn't matter. So we might actually talk about semantics. Not your kind of semantics, just amateur semantics. So again, these parser combinators, what is it that actually makes them really cool? Even in the horrible Japanese notation. What is the real issue here? It isn't about the syntax, it's about the fact that they work so well for describing and building something that actually executes and will parse a program. So lovely system for doing it. And the reason it works so well is because it's compositional. And this is one of the very key ideas in programming languages, and what makes them powerful and interesting if done well. And the point is, it's a lot like algebra. Right? You have this set of values, and you have some operations on it. And it's very important that you have a uniform set of values. Then you have operations that take some of these values and produce new ones that are in the same set. So it feeds back on itself. So you can build more complicated and richer values out of those basic values. And therefore it grows. And if you have this set, then this space is essentially infinite, which helps it deal with a wide range of issues. In this case, we only had there are only a handful of operators in this thing, right? There are, there's sequencing one thing after another, which actually doesn't even have an operator. It's just implicit in the notation. And that's generally a good idea. If your most common operation should be implicit in your notation, because you don't have to repeat it all the time if it's happening all the time. And then we have alternation, one thing or another. And we have this star, which is handy for repetition. There's also a plus for repetition. This is 0 or more, plus is 1 or more. There's usually like a question mark or something for something that's a single optional occurrence. And that's about it. And the thing is, each of these operators, basically is still a recognizer. It's still a parser. The basic building block of space here is things that parse a single letter or parse a single digit, etc. And then we get a parser that parses either a letter or a digit. And then we get a parser that parses a whole sequence of them, maybe empty. and then we get one that parses first the letter and then the sequence, right? And we compose bigger and bigger parsers, and the same operators will apply to them, and so we can build a big grammar for a big complicated programming language, and we can describe a language with as big a grammar as you want. We can describe Java or C# or PL1 or you name any of Ludwig's many castles in the programming language world, right? And we get that from this compositionality. And this is something to look for, because if you do it differently, if you don't make it compositional, if you say, can't you just adjust it for me in this one special case? Special cases are the plague. Users are always coming to you because they have a specific problem and they want some dispensation, some special treatment. But what happens then is your special cases compose, and the surprises and the mismatches start to grow into an infinite space of problems rather than the actual working stuff. But the temptation is there, and the vast majority of both people who use programming languages and engineers who build them don't understand this. So, as an example, I'm going to give you something that's kind of almost a historic relic. I'm sure somewhere there's some APLers who kill me, but unfortunately APL is kind of it's a programming language that's pretty much at the fringe at this point. At one point it was a very hot ticket. IBM pushed this very hard in the 70s. They actually had products, they had manuals, there had enormous resources. It was a real going industrial thing. That's almost as fashionable as you know, C# might be today. So the difference is, however, that there's still stuff worth learning from it. And so this again was actually invented originally as a mathematical notation. I think Iverson, the man who invented this, originally didn't even, wasn't originally very concerned with making it executable. And it's very similar here in that it's compositional. It's based on composition, on operators, on arrays. And that's it. So arrays are a very general structure. You can have arrays with one element, you can have scalars, you can have vectors, you can have matrices, you can have bit vectors, you can have truth tables, you can represent board games, you can do graphics, right? There are a lot of things that fall into these 1 or 2 or 3 dimensional structures, and of course APL will cope with as many dimensions as you want, right? But they all compose. It's very, very uniform. And it's a different way of thinking. It actually, now it's been 30 years since I wrote any APL, so I had to look at Wikipedia to actually look up an example and try and figure out how to explain it. But the fact is, it gives people a different perspective. People who really have gotten good at it, they think differently. And that is really what you want out of the programming language, is that it will actually give you the notation will give you leverage, that you will give a way of thinking. So this is an example. This is an APL program that computes all the primes up to R. And it is eminently readable, as you can see. Now this was always a complaint about APL, that it is an incredibly dense notation, and unless you're comfortable with it, it looks like something that came from Mars. Now, the fact is that C looks like something that came from Mars. Perl certainly looks like something that came from Mars. And this hasn't necessarily stopped them, right? People are incredibly adaptive to these notations. If they're motivated, if they are trained, they can learn. And people who got good with this could do amazing things. The difference from Perl is this is not some haphazard collection of stuff, right? So let's go through this and see what it means. Well, we'll start with R. We'll set R to 6 and figure out all the primes up to R. So the first thing here we have in red here, this guy, Yoda R, this basically takes some number and gives me a vector from 1 to that number. So here we are, 1 through 6. And the next thing we do is we drop the first element. That's what this stuff does. Drop first element, you have 2, 3, 4, 5, 6. That's because 1 isn't very interesting when you're looking for primes. And then we have this assignment arrow, and we're assigning this new vector computed to R. Now this is also showing APL's age and style, because this is a horrible thing to do, right? We're overloading, we're using the same name for 2 different things. God knows why, but it's kind of typical of a mindset. So there's certainly problems with it. But now we've set R to be this vector. And the other weird thing, you notice this is being evaluated right to left. Gives me an advantage. It's a Semitic language, essentially. So, next, we start on the left-hand side. This thing is some sort of fancy outer product, and basically gives you the tape, it multiplies the vector with itself. So all the elements in the vector with all possible multiplications with the other elements, right? So you get basically a multiplication table. Right, so these are all the ways to multiply the elements from 1 through 2 to 6. Okay? And now, the next guy, it basically takes R and gives you essentially a bit vector of where those places in R where an element in R was actually found in this table, right? So, where one of R's elements between 2 and 6 actually occurred in this guy. And we find that this is 2, 3, 4, 5, 6, and 2 and 6 actually occurred in that table. Because they're actually results of multiplying things that happen. Which tells us that the other guys that can't result from such a multiplication are the primes we're looking for. So in order to home in on this, well, we'll flip the bits. That's what this negation thing does. And now we can go operate on R here with this guy, which will basically do a filtering operation for where the truth values, the ones are old. And here we are. Right? Now, this might not have been the most obvious way to go about this problem. But it's a different way of thinking. You'll note that it is completely parallelizable. Right? There's no sequential anything really going on here. Right? There are no your usual ifs, and it isn't Fortran in new dressing, which is basically what we've been using for the most part since 1955, and certainly what we're stuck with today. It really is a different way of thinking. And the fact that, it's going extinct is in some sense a great loss. But it is enormously powerful. I mean, this is an example I could fit on a slide, right? So another one of those examples is like Conroy's game of life. In a line. Okay? Now don't ask me to explain that line, but there are explanations online, and we probably have spent the hour going through that. But that's why people really loved this thing, because it was really, really powerful. You really could do a lot of complicated things very concisely without really getting bogged. Once you learn to really think in APL, then you didn't get bogged down in sort of sequential stuff. And it derived its power from composition. So, a few, the other great source of computers of programming language, quotes, is Dijkstra. And in particular, this essay of his, which is full of nice, thoughtful things about other people's work. There's something to be said for that. On the other hand, Perlis actually taught APL at Yale, and had nice things to say about it, because there are nice things to say about it. I'm not saying it's perfect. There are modern dialects, I think, that where some of these things have been adjusted. I can't claim to follow it. But I figured that given the laws of diversity, I could spend part of my time here subjecting you to this, just so that, my guess is that most people here have not heard of APL and are not familiar with it. And there's a whole lot of things like that. There's this whole world of, trilobites and other extinct creatures, dinosaurs, all kinds of really interesting creatures that can expand your mind. Just to, again, for reference, just to calibrate Dijkstra, in case you're not using the quotes, here's another one that's very accurate. And alas, that essay was written like circa 1975. We don't have his, kind words on Java and JavaScript and Perl and Python and all the rest of them. I'm sure he would have very nice things. The great thing about quotes is you can ascribe them to someone else. I said that. So, I want to talk a little bit about something going a bit outside of just languages, but systems. Because people get confused between languages and the systems that implement them, and there's good parts to this and there's bad parts to this, right? You notice when I did this APL thing, right? So I've created these slides and I'm showing you step by step what it's doing, right? You see the evaluation, you see intermediate results. It helps you follow what's going on. So that's a nice thing, and wouldn't it be nice if there were systems that actually did that for you? Well, APL systems actually did, for example, right? APL was always an interactive system. And even in circa, 1970 or whenever, there was an interactive workspace. You would evaluate something, you'd get a result back, you'd see what was going on, right? Even, there were line numbers back then, and it would give you fractional line numbers when you decided to edit your program and stick a line in the middle. It would give you line 2.1, things like that. It was interesting. We've actually regressed on that, right? But the systems that implement this are important, and most people actually have the opposite problem. They don't distinguish between the language and the system. If you're a language person, you know that it's important to realize that whatever thing you're running is one incarnation of this language. It's a particular implementation. Maybe it's the only one, but the language itself is a concept that's separate from that and could be implemented in different circumstances in different ways. Most people tend to identify the artifact that they're working with the language. And so you hear inane statements like uninterpreted language. Right? If anybody talks to you about an interpreted language, they haven't a clue what they're talking about. There is no such thing. There are languages whose implementation happens to be an interpreter. Okay? It's not the same. You could compile this. So actually, I remember being told that APL could not be compiled, because APL has some nice reflective things where you can feed code into itself, right? It can't be compiled in advance, but you can have a dynamic compiler. In fact, APL pioneered, the first JITs on this planet were in APL in the 60s. Right? So don't let anyone tell you that, say, Java invented any of this stuff. So these are artifacts, and the language may be implemented in one way. There may be a compiler, there may be an interpreter, there may be an ID. Maybe you need an ID, maybe you don't. But this is all part of a particular implementation, particular system. On the other hand, systems are really important, because when you're just studying the language, then you're missing a lot about how this is actually used as a tool, what you can actually get out of it. For example, the ability to actually interact and get feedback and see what's happening when you're writing a program, evaluating things and seeing how the steps work, right? And I want to make this point because it's underappreciated. And in particular, the point, this interaction, this is one of the many system properties one can talk about, but this one, which I'm going to put under this banner, liveness. Right? Liveness is not the race condition kind of concurrency study thing that you've no doubt been, at least the grad students in computing here have probably been subjected to. Right? It's important, but then we're talking about something again completely different. Back to this is more a vague concept, an artistic concept, if you will, right? It's the fact that you can interact with this. Again, it's a concept you have to feel in your bones. You have to work with systems that have this property, and then you go back and work with, say, Eclipse, and then you realize what people mean when they say it's dead. Right? It's the difference between a computer as a system you can interact with. It can give you results. It's dynamic. It's moving in time. It's not a piece of text, a piece of paper that's just fixed. Right? And if you build tools around programming languages that basically present you a glorified piece of paper, then you're missing something, because it's about the dynamics. It's about what you compute, not about the static analysis of what you compute. Which is, in a lot of these environments that you see today, if you're used to these tools, it's the emphasis on the static is sometimes useful, but it's greatly overemphasized. So in the interest of doing this, I decided I'd give you a little demo. So let's see how big we can make this. I get that. Can people see that? Okay. Okay, let's see if we can actually move this a bit. Maybe I can make it. I don't want to keep the button. Okay, this is about as far as we can go. right? So this is actually a very similar program to the APL one. I don't have an APL environment on my Mac, and I don't know how, I probably couldn't work it if I did, right? So I'm going to give you an example of an environment that's live, right? A system. Because the programming language in question here, which is Newspeak, which is a descendant of Smalltalk, which is another one of those languages that is marginalized, but which there's a lot to learn from, is a live system. In fact, it's very important. That's one of the big things the Smalltalk perspective gives you, is a live system. Because again, if people have a hard time separating the Smalltalk language, which could be rendered as dead as Java almost, if you know, with a text editor and things, but historically isn't, right? It's a cultural thing. It has always been part of an interactive environment. And so we're going to do the same thing, except we'll do this, and you can see the trade-off in notation, right? This is not as concise as the APL. On the other hand, you might actually understand what you see, which has arguably some advantage. So what we're going to do is we're going to, we want a vector from 2 to 6, right? Remember, we got 1 to 6, and then we dropped 1, because those were the operators APL gave us, but now we were actually after 2 to 6. So evaluating 2 to 6, if we go look at 2 to 6, what do you know? 2, 3, 4, 5, 6, right? And again, this is something we can, now we have a problem that, go back.